Okay, in this video I'm going to talk about the Simson line. So let's say that we have an arbitrary triangle, and we consider the circumcircle of this triangle, and then we consider an arbitrary point on this circumcircle. So let's say we have this point. So let's then we consider the altitudes from this point to the sides of the triangle, or more precisely to the lines containing the sides. So these altitudes can fall either to the sides or to the extensions of the sides. So in this case, on one extension and on two sides. And so then the theorem is that these 3 points, the feet of these altitudes, they lie on a single line, and this line is called the Simson line. So let's denote the points. So the original triangle would be ABC, then these points denote the arbitrary point that we took on the circumcircle, denoted by X, and then the feet of the altitude, let's denote them like, let's say, P, Q, and R. And so the theorem says that P, Q, and R are collinear. Collinear meaning that they lie on a single line. Or like, yeah, because we need to introduce the name of the line, let's write it as so they lie on a single line. Which is called the Simson line. Okay, so let's prove this theorem. It's actually not very difficult to prove. Just some calculation of angles. So I will consider only one configuration of points. So like there are several cases depending on which, like where we pick this point X, like these altitudes might fall on the sides or on the extensions of the sides. So the configuration is slightly different. The proof is generally similar, but it might differ in minor details. So I will consider only this case that is shown on the picture, and the other cases are considered similarly. So basically we observe that the quadrilateral PQ XA, so this quadrilateral that I highlighted in blue, so this quadrilateral is inscribed because like we have the angle APX is equal to the angle AQX. And both of them are equal to 90 degrees, but this doesn't matter in this particular case. So what is important is that these two angles are equal to each other, and this is one of the criterion of the cyclic quadrilateral. So this quadrilateral is cyclic. APQX is cyclic. So because it is cyclic, we have the equality of angles, the other angles. So let's say this angle is equal to this angle, right? And let's denote this angle by x. Right. So now consider similarly the quadrilateral XQCR, this that I highlighted in green. So it's also cyclic because the opposite angles are 90 degrees, so the sum of these angles is equal to 180 degrees. So this is also one of the criterion of the cyclic quadrilateral. So we have the angle XQC plus the angle XRC is equal to 90 degrees plus 90 degrees is equal to 180 degrees. Therefore, XQCR is cyclic. Because it is cyclic, we conclude the equality of angles. Yeah, here we can also, like I showed only on the picture, but we can write it also here. We concluded that the angle XAQ is equal to the angle XPQ, and we denote it by X. And here we have, or let's write it here. We have the angle, so let's draw this diagonal here, and we consider the angle yeah, let's draw both diagonals, and we consider this angle is equal to this angle because they subtend the same arc XQ in the circumcircle of this cyclic quadrilateral. So from because it's cyclic, we conclude that the angle XRQ is equal to the angle XCQ, and we denote it by y. So we denote this angle by y. Okay. Now let's denote also the angle B in the original triangle by beta. So now we notice that the like in the circumcircle of the triangle ABC, so in this circle that is shown on the picture, the arc AC is equal to 2 beta, so it's twice the inscribed angle beta that subtends this arc, but on the other hand it's equal to AX plus XC, and each of them is equal to X and Y. So the arc AX is equal to Y, to Y, twice the inscribed angle Y subtending this arc, and the arc XC is equal to twice the angle X, so the angle XAC subtending this arc. So when we sum them together, we get, on the one hand we have beta 2 beta. On the other hand, we have 2x plus 2y. So let's write this. So basically we say that the arc, so the angle, so 2 beta is equal to the arc AC, because it subtends the angle beta is an inscribed angle that subtends this arc AC. On the other hand, the arc AC is the sum of two arcs AX plus XC, and AX is equal to 2y. The angle ACX is the inscribed angle that subtends this arc, so it's equal to 2y plus XC is equal to 2x. So in total we have x plus y is equal to beta. Now let's now find the angle PQR. So this angle PQR, so we consider the quadrilateral QPBC. So let's denote it. So basically this quadrilateral, not BPQR. So this quadrilateral, right? So so we are interested to find the angle PQR. So PQR can be expressed as the angle PQR can be expressed as 360 minus the three other angles of this quadrilateral. So 360 minus the angle PQ plus minus PBR minus BR Q, right? So now let's express all of them. So 360 we rewrite as this. Now BPQ, so this is this angle BPQ, so this angle. This angle is 90 degrees minus x, because this angle is x, this angle is x, so and this is 90 degrees. So this angle is equal to 90 degrees minus x. So 90 degrees minus x. Now PBR, this is simply beta, we denote it by beta. So minus beta, and BRQ, so this angle is simply 90 degrees minus y, because this angle is y and this angle is 90 degrees. So it's 90 degrees minus y. And in total we have, so we have 360 minus 90 minus 90, this would be 180, right? Plus x plus y minus beta. Now this x plus y minus beta, this is simply 0 because of this, because x plus y is equal to beta, right? So therefore this expression is simply equal to 0. So in total we have 180 degrees. So the angle PQR is equal to 180 degrees. What does it mean? PQR is 180 degrees. This exactly means that PQ and R are collinear, or lie on the same line, on a single line. So this immediately implies that P, Q, and R are collinear, and this is exactly what we needed to prove. So this concludes the proof. So that's it for this video.